We will discuss about network flows. We will see the problem of maximum flows, and we will study several algorithms for solving that problem. The augmenting path algorithm, which is the Ford Fulkerson algorithm. And then we'll see two improvements that we can do. And one idea to make it strictly polynomial will be the idea of scaling algorithms. And then we'll see a slight variation of that problem, which is the minimum cost flow problem, which is more or less the same problem, except that in addition to maximize the flow, you also want to minimize the amount of cost, since you have also a penalty to pay for every flow that you push that might be different in every edge of the graph. And we'll see that we can reuse this idea of iterative shortest path problem. Then we will see the link between flows and linear programming. Let's start first with a little bit of background. Okay, so the max flow problem is a combinatorial optimization problem on graphs. Many problems can be solved with the max flow on a graph, and you can find application in transports, distributions, network designs, for instance. It's a very useful building block in general, and you may find this building block in many different contexts, especially in optimization. For instance, it's sometimes used to generate cuts in mixed integer programming, but it's also used in constraint programming, for instance, to design filtering algorithms, such as for the all different constraints, but not only. If you remind your data structure and graphs algorithms, a graph is something like that. You have nodes, you have edges, right? V is a set of nodes, and E is the set of edges. And we will assume that these edges are directed edges. Okay, so we will represent a pair AB as a directed edge from node A to node B. This is a small example of a directed graph, for instance, with 4 vertices and 1, 2, 3, 4, 5 edges. You might also have weighted directed graphs, and in addition to the edges, you can also find weights on the edges here. Okay, and so for every edge, you have a function here, f, that gives you the cost of using the edge represented here. For instance, from 1 to 3, or from 3 to 1, you pay 6. From 4 to 1, you pay 9. Okay, it can represent the distance. It really depends on the application. It can represent distance, the cost, the capacity, or whatever. A path is a suite of distinct nodes, such as node 0, node 1, and so on. Okay, so each of these are a different identifier of the graph. And of course, for every consecutive node on your path, it must be that this is a valid edge of your graph. Okay, we call N0 the origin of the path, and the last one will be the destination of the path. A cycle is also like a path here, a suite of distinct nodes. Okay, but at the end, you come back to the first one. Okay, this is a cycle. Sometimes, in some textbooks, you will find that paths and cycles are identified with a sequence of edges instead of the sequence of nodes, but it's really the same. So then we can, and if you remember from your data structure course, how can you implement an abstract data type for graphs? First possibility is the adjacency matrix. Right? The adjacency matrix is simply a Boolean matrix, which is a V by V matrix, and you simply put between the entry I and j, you put a 1 when there is an edge between 1 and j, and if there are no, you put 0 everywhere. All right? So you have 0 and you have 1 only when you have an edge. Okay, this is what I represent here. So in this adjacency matrix, MAB is equal to 0 if the edge AB does not exist, and if the edge exists, you put a 1 here. The drawback of that is that the amount of memory that you use will be will always be order of v square, right? Or theta v square. So this is quite a lot of memory to pay if you only have a few edges, for instance. And a few edges, we mean by that we mean that the graph is sparse. So in that case, we prefer to use a linear time complexity, and this is also better if you want to iterate, for instance, out of all the adjacency nodes to a given node. Okay, so for instance, if you have the node I, and you have only a few nodes going out of that one, you have, for instance, J, K, L, okay, and you want to iterate over the adjacency node here. Instead of going through all the nodes and having to parse all the row of the data, we would like to have something which is proportional, which is linear in the number of adjacent nodes. And this gives us the next possible implementation, which is adjacency lists. In the adjacency list data structure representation, you will store for every node the adjacent nodes. So for instance, what are the nodes adjacent to node 3? Well, there is, of course, 1 and there is 2, right? And this, therefore, you have a linked list that says 3 has 2 neighbors, first 1 and then 2, okay? The order that you will see here is completely arbitrary, right? It doesn't matter. It just allows you to iterate over all the adjacent nodes of a given node. You can implement that with a double linked list or a simple linked list. Anyway, whatever you want to use as a collection is good in the adjacency list.